We're going to be talking about isomers, and before we really jump into this in much detail, we want to kind of get a handle on what isomers are and what the subtypes are. Isomers are organic chemicals, compounds that is, that have the same empirical formula, like C3H5N. Okay? And they can be broken down roughly into constitutional or structural isomers and stereoisomers. Now, structural isomers have atoms bonded to different atoms. So in this case, the fluorine is attached to the second carbon in from the right. In this case, the fluorine is attached to the terminal carbon. So there are different points of attachment. Those are structural isomers. Now, stereoisomers are situations where you have the same bonding of atom to atom, but the arrangement in three-dimensional space is different. And that's a little tricky. We're going to go over that in detail, but here's an example of a single carbon molecule where the arrangement is different in space. And these kind of isomers are called enantiomers. So let's kind of back up a little bit and consider the fact that molecular atoms and molecular structures are three-dimensional. And often when we see a structure like chloromethyl alcohol here, chloroethanol, we often think of it in terms of two-dimensional. Indeed, it's often represented that way. And when you see it with just these straight line bonds, you don't know what the stereochemical configuration is of that molecule. Now, sometimes you'll see it written in this way, where the one of the two atoms that are bound to carbon that are designated with a straight line are considered to be in the plane of the paper, and the one with the wedges coming out and the one with the dashes going away. We're going to talk about that a little bit more later. But this is kind of a two-dimensional representation as best we can of the 3D structure. And lastly, you can represent a molecule in this kind of way as sort of a space-filling representation with shadows on it that is meant to show as best it can that there are certain atoms, for example, this hydrogen here and this oxygen, that are kind of in the plane of the paper, whereas this chlorine is coming towards us, and then this methyl group is going away. So I tried to draw these in a way where the simulated 3D is the same orientation as the three-dimensional structure. So let's discuss some terms that are used in stereochemistry. One is the idea of stereoisomerism itself, and this occurs when molecules that have the same type of atoms and the same bonding location of the atoms have different arrangements of the atoms in three-dimensional space. Those are stereoisomers. Now, stereoisomers typically arise in small molecules from compounds that have a chiral carbon, or compounds that are chiral, sometimes called handed. Okay, and these compounds lack what's called a plane of symmetry. There's no way to take a molecule and bisect it into two equal halves. Now that's a little bit difficult, I know, for students to kind of get a handle on, and a simpler way, which is really the same thing for compounds that have one chiral center, is that the carbon atom in a chiral compound will have four unique substituents. So you can pretty much, in terms of our study in pharmacology here, look at a compound and look to see which carbons have four unique substituents. Those are the chiral centers that give rise to the stereoisomerism. Now I have a video here which accompanies this narrated PowerPoint that kind of, I hope, does a decent job of demonstrating this. Enantiomers, these are, okay, when you have a chiral compound, there are two different stereoisomers that arise from that chiral compound. And those two stereoisomers are known as enantiomers, okay? They are mirror images of each other. Now, if you have a drug, let's say, that's a 50-50 mixture of the two mirror images of the two enantiomers, that is known as a racemate or a racemic mixture. If you have, that is actually a drug composed of two different chemicals in a sense. Now, if you have a drugs that has only one of the two possible enantiomers in it, that's a homochiral drug. That's just how it's defined, homochiral, only one enantiomer. Now, getting back a little bit to those bond designations we use for stereochemistry, you see we can have the atoms that are bound to carbon that are in the plane of the paper are indicated with straight lines. The atoms that are behind the paper, behind the plane, are the wedge, and then those are that in front are those that are behind are the dash, and those that are in front are the wedge. Now, if we have a mirror that we put alongside the side of one of these kind of compounds, that's a chiral compound, right? It's chiral because it has four different substituents. We see that we can reflect that image to this other compound, which is not superimposable. You can't put it on top of you can't put B on top of A. And this molecule then is the enantiomer of A. So the two of them are enantiomers, okay? Now, sometimes we'll see a drug structure which is drawn with only straight lines. This example here, we see that we have the dash, and the dash and a wedge shown, right? But if these were just straight lines, it would indicate, in general, if you see a drug product in a package insert that just has straight lines, it indicates that you can presume that it's racemic, that the drug product has both enantiomers. Okay, so I have a series of questions here that I'd like you to kind of contemplate, stop the narration here and think about these. And then when you're done, come back and we'll go through some answers. So let's take a look at these individual questions. Which, if any, atoms in each of the molecule is chiral? Well, the only atom that we really consider to be chiral would be a carbon, so we have to look at the two carbons. So let's look at the carbon here. Okay, we're looking for carbons that have four different substituents, and clearly the methyl and methylene and the methyl don't have different substituents. They have more than one hydrogen. But this carbon has 1, 2, 3, 4 different substituents, so that is a chiral carbon. Okay. Now, in this alcohol here, we have a carbon here that has 1, 2, well, let's see, these are equivalent substituents, so this only has 3 different substituents. So this one is not chiral. How many stereoisomers, if any, can each molecule have? Well, it's important to remember that a compound has to have chirality in order to have stereoisomers. Now, there are more complicated cases of molecular chirality we're not going to get into here. We're just talking about traditional simple small molecule drugs. And so we don't have a chiral center for the molecule on the right, so we're not going to consider that. That is not stereoisomers at all. Any way you hook these substituents onto the carbon, you get the same thing. You get compounds that are superimposable or that are identical. Now here we find that we do have the chiral center, and we have 2 to the n possibilities, which is 2 to the 1 possible stereoisomers, which is 2. Now, how does chirality even come about? I want to just take a minute to look at this. When we think about compounds that are biosynthesized, they're made from nature, almost always formation of a chiral center occurs in such a way that you only get one of the 2 possible enantiomers. That is, you get a homochiral product. So here's an example of a reaction. Don't worry about the example where a hydrogen comes into this ketone and reduces it to an alcohol. And because the hydrogen comes in from one side, see the molecule is locked in place by an enzyme, so the hydrogen comes in at one side, and then you end up with one of the 2 enantiomers of the alcohol. And you're going to see that biosynthesized compounds like alkaloids, morphine, or steroids all have each of the chiral centers specified as one of the 2 enantiomers. However, chemical synthesis is a little different. We get generally a mixture of, when we have formation of a chiral center, 2 enantiomers, the racemates. So what happens here is that the reducing agent, whatever that happens to be, can kind of attack, in this specific example, from both sides, leading to the OH forming, either coming towards us or going away from us. And so 2 enantiomers are formed. The important thing for you to remember is that quite often in chemical synthesis, when drugs that are made through chemistry often tend to be racemic, whereas almost anything we get from nature tends to be homochiral. Now, I just wanted, for sake of completeness, talk about compounds where there's more than one chiral center. These compounds, well, all compounds that have chiral centers have 2 to the n stereoisomer possibilities. So if you have one chiral center, 2 to the 1 is 2. Right? We've already talked about that. If you have 2 chiral centers, 2 to the 2 is 4. You have 4 possible enantiomers, or excuse me, no, 4 possible stereoisomers. If the stereoisomers, okay, in compounds that have more than one chiral center are completely mirror images of each other, okay, you have 2 compounds that are completely mirror images, those are enantiomers, okay? Enantiomers are always mirror images of compounds that have chiral centers. Now, you can also have cases where you only have part of the molecule being a mirror image. So those compounds are called diastereomers. I know that's very confusing, and I wouldn't be too concerned about it. The main thing is to focus on compounds that have one chiral center. I'm just doing this for sake. And just to kind of really beat this to death a little bit, just if you can follow this, you can. If you can't, not to worry. But here's ephedrine. You see it has 2 chiral centers. And here's the enantiomer of ephedrine, where both chiral centers, you see, have the reverse stereochemistry, okay? So that is, in fact, the mirror image. But here's a situation where the carbon adjacent to the ring here has the same configuration as ephedrine, but the other carbon is the mirror image configuration. Okay, that's really a stereoisomer that is not a mirror image. That's called a diastereomer. Okay, so Thing to remember, stereoisomers that are not mirror images are diastereomers. Simple. All right, back to enantiomers, which is really our main concern. Okay, simple situation when we have one chiral center in a molecule. We need to be able to designate unambiguously the identity of the individual enantiomers of a drug. Now you may wonder, well, why? Why do we really need to do that? Because if a chemist is synthesizing a compound or producing it in Germany, he or she needs to be sure that they're making the proper stereoisomer, the proper enantiomer that is in the drug product. So you need a way to be able to specify which of the two enantiomers you're talking about. Now there are two ways to do this. One way is to take the compound and put polarized light through it and see which way it rotates the light. We're going to talk about that. The other way is the so-called absolute configuration method. Well, what are these things? Well, one is the polarized light method. In that case, we take the drug, put it in a solution of water or something like that, and then shine a polarized light through it. So this is in a polarimeter. This is an instrument that takes polarized light, and basically you can see that it's coming in here. Here's the plane that it's coming in, and it's bent a little bit, right? And and this is purely an empirical kind of thing. It's just an experimental measure. And if it bends the light towards bends it towards the right here, that's called a dextrorotary compound, or plus, given a plus sign. And if it bends the light towards the left, or counterclockwise, that's a levorotary compound, or minus. All right. So again, something that's empirical, it's actually a measured value, and we have this D or L designation, which is identical. It could either be called D or plus, or L or minus. Okay, D and plus are two different ways of saying the same thing. L and minus are two different ways of saying the same. Now, the other way we can talk about a configuration, the arrangement, spatial arrangement of atoms around the chiral carbon, is according to this kind of arbitrary, agreed upon set of rules that have this fancy name, Kohn-Engel-Prelog rules. Those are the three organic chemists that came up with the idea. And notice I have FYI here, meaning that I don't expect you to memorize this and be able to do it. Okay, that's just not, to me, it's not a priority. All right, but I want you to at least have an idea of how it's done, so you see that what the logic is. Okay, and basically we're assigning priorities to the different substituents, calling them number 1, 2, 3, and 4, depending on their atomic weight. Then we orient the compound in a certain way, such that the lowest priority substituent is towards the back of the paper, and we draw a circle from priority 1 to 3. If the circle is clockwise, it's called R. If it's counterclockwise, it's called S. So this is just an arbitrary set of rules, but it unambiguously assigns a name to a particular enantiomer, and it has value in that sense. Now, I do want you to keep in mind that there's no relationship between the absolute configuration and polarized light rotation. Okay, you can have absolute configuration R and S can be R can be D, R can be L, or vice versa. Okay, there's no relationship between the two. Okay, so you could try this on your own if you want. Just click on the picture and you get a nice little molecule that you can rotate in space. Now, what are some interactions of enantiomers? Why do we care all this stuff about enantiomers? I mean, aren't they like virtually identical? No, they're not. Their interaction with chiral agents, and I know that's a kind of a nebulous term, but anything when they interact with something that has a handedness quality to it, okay, such as an enzyme or a transporter, you're going to get a different action. Think of it this way. Okay, if you have a hand interacting with a glove, okay, the hand, let's say, is the drug, and the glove is the chiral agent, the enzyme, whatever. The hand interacting with the glove, it matters. If you have a right-handed glove, you're not going to get it to interact very well with a left hand, okay? But if you have one of these gloves that's ambidextrous kind of glove, right? It has no handedness to it. Well, that will work just as well with a left or a right-handed glove. And this is in the demonstration I have that it goes with this lesson as well. Now, interaction, as I say, interaction with achiral probes, that is like a hand interacting with one of these uh, either or kind of gloves, the ambidextrous glove, it won't matter. So if you have an R and an S enantiomer going through a lipid bilayer, they both get through equally well. Okay. Now, here's an example of the difference, for example, of activity of some beta-adrenergic blocking agents. And when you get into P2, I'm going to show you the same table. But you see, this is a list of different beta blockers, okay, and relative activity, the relative beta blocking activity of the plus and the minus enantiomer could be called the L or the D. All right, and let's just look at one. Let's look at propranolol and notice the difference between the minus and the plus enantiomer. One is 100 times more potent, if you will, than the other. So this is one of these fundamental points I really want you to understand. It matters which stereoisomer you have in terms of its receptor and enzyme interaction. Okay, if you have now, how about if you have a racemic mixture of propranolol? Well, it's going to have basically one component in it which is active, the minus enantiomer. That's going to have the plus component, 50%, which is essentially doing nothing, maybe even doing something bad. So in order to get away from this problem, drug development has trended towards development of single enantiomers. And so if we I know that's a complicated kind of a slide, but if you look over time and you look at racemates, how many racemates are being developed and released by the FDA, you see how it's going down, right? Over time. And the single enantiomers are going up because having a racemic compound is having a mixture, okay, of essentially two molecular entities that have different half-lives, different activities, different toxicities, and you really don't want to have that. That's too messy. There's actually even been a move. Some people are making a lot of money. There are companies that do this full time. They actually take older drugs that are marketed as racemates, and they cull out. They simply get a modified NDA for the one particular enantiomer that is responsible for the activity. Now, you might think, oh, my goodness, why not just always do it that way? Remember, go back to the synthesis. It's very difficult to synthesize single enantiomers. Very difficult. In fact, quite often what's done is the chemical production that makes the racemate. For example, let's look at salbutamol here. Right? This was probably made by reducing a keto group, in which case we got both enantiomers of the alcohol. And then what you have to do is resolve or separate those two enantiomers. Complicated, expensive process. So, however, at the end of the day, if you've got a safer, more effective drug, it can be worth it. So that's called chiral switching. And here are some cases where you see the original racemic drug and then the individual enantiomer that was developed. And you may notice here that in some cases we've got this designation and R designation, which is that absolute stereochemistry, and then sometimes we have like leva butyrol. That has to do with the direction that it turns polarized light. Separate thing. Okay, so test yourself. Go back. I should say stop the PowerPoint and see if you can answer each one of these questions, and then come back and we'll walk through them. But really, take a minute to look at them yourself. Okay, so which of the following would interact differently with the two enantiomers of a compound? Water solubility. Would you expect the solubility of two enantiomers of a compound to be different? Well, is water a chiral probe? If you look at a molecule of water, you'll see it's really a planar substance. So the answer is no, the two would be the same. They would be expected to have the same solubility. How about plain light, just regular light? So you're looking under a microscope and you're looking at crystals of, let's say, the R and the S enantiomers of a drug. Would they appear different? Plain light does not separate it does not have handedness. It doesn't distinguish between the two. Polarized light, now that's a different case. That polarized light does have optical rotation. So there, yes, we would see a difference between the two. And if you've ever seen compounds that are chiral, quite often you'll see stunning photographs of them through polarized light. It's really quite pretty, but you can certainly differentiate in that way. In fact, we've talked about that as a way to characterize the enantiomers. How about heat? For example, melting point. Would it be different between the two? Well, heat is a chiral probe, so no, it's not going to be different. How about acid-base environment? Extent of ionization. If you have a carboxylic acid that has two different enantiomers, is the extent of ionization, say at pH 3 or whatever arbitrary pH, going to be different? Well, acid-base environment is not chiral, right? It's nothing chiral about it. So the extent of ionization would be the same. Now how about a metabolic enzyme? An enzyme definitely cares if you're R or your S, what the enantiomers. Okay, that's very important. Yes, that's a chiral probe, if you will. So interacting with a metabolic enzyme is definitely going to be different for the two enantiomers. And indeed, we often find that the half-life of two enantiomers in a racemate is different, which again contributes to the complication of understanding how the drug works. And transport proteins, we're going to talk about that later in the course, but these are proteins that move around drugs and really nutrients in the body, and drugs just happen to take advantage of those transport proteins. Yes, there's a particular interaction that transport protein has with one enantiomer that it does not have with the other. So yes, there will be a difference, and it is a chiral probe. How about taste? How about your tongue? I hope you can imagine that. Yes, that has receptors for particular chemicals, and can easily distinguish between the two enantiomers. In fact, we can look at these two compounds here, spearmint and caraway, which are enantiomers, right? They have one chiral center, and these are the opposite enantiomers. One of the one enantiomer, the one that's designated R, has a spearmint taste, and then the other one has a caraway taste. That's radically different because they interact with the receptors on your tongue in a different way. Okay. Here's one more case. Test yourself. Propranolol, timolol. Okay. Take a minute, stop the tape, try to answer the questions. How many chiral centers are present? Well, let's look at this molecule. Remember, we're looking for 4 different substituents. No, nothing here, nothing here. Bingo, there's one. Now 2 hydrogens on that one. So it's got 2 methyl groups now. Okay, so here we go. We have 1 chiral center here. How about timolol? Okay, 2 hydrogens here. Oh yeah, that one's got 1, 2, 3 hydrogen. That's chiral. It's got 2 hydrogens. It's got 3 methyl groups. Tertiary methyl T-butyl group on it. So it has 1 chiral center here for timolol and 1 chiral center here for propranolol. Okay. How many stereoisomers are possible? Okay. Remember, the number of isomers that are possible is 2 to the n. So in each case, we've got 2 possible stereoisomers, or 2 enantiomers. How many stereoisomers are in the actual drug product? Okay, so I'm assuming here that what we have is propranolol and timolol, the structure designated as it appears in the package insert, okay? And that represents the molecules or molecule that is in the product. So let's look at timolol. Even though timolol has a stereocenter which can go, that OH can be towards us or away from us, we see that the drug product only has the molecule with the OH coming towards us. So there's only 1 stereoisomer in timolol. Now, propranolol, they didn't really say. They just have a straight line here, okay, as opposed to the wedge here. They just have this straight line. Now, what that means is that it's either way. They're not specifying because the drug has both the OH coming towards you and OH going away, both enantiomers. That one is racemic. So how many stereoisomers are in propranolol? 2. How many are in timolol? 1. Based on the structure as it appears in the package insert, which I've reproduced here. Okay, guys, just a little fun. You can take a peek at this. But that's it for now. Take a few minutes to look at the accompanying video. I think it's kind of fun. Okay, God bless. Take care.